This video shows you how to set up a problem involving matrix diffusion, of transport along a fracture, and then diffusion into and out of the matrix. So we need a chemical species transport, and we're going to use transport of dilute species in porous media. So we select that physics, and we also need to calculate the fluid flow. So we're going to go and select Darcy's law for the fluid flow. Now the definitions, we've got two domains, fracture and matrix, and I'll show you how those are set up. It's two domains. You can see this is just like a vertical slice of rock with a fracture right in the middle. The first domain, block 1, is just a slice of rock with those dimensions. And then the second domain is a narrow rectangle, and that's the fracture. The width is, I think, 1 centimeter here. We've got water as the fluid, and then Darcy's law is set up like this. The dependent variable is P. The fluid is the water, and the porosity and permeability are set up with those two variables called porosity and K. And I'll show you more about those in just a second. The inlet velocity is specified there, and that's on the left side, and on the right side we specify the pressure. The hydraulic head is 0. And then the transport physics are set up where we specify the porous media, and we've got to make sure to import the fluid velocity from Darcy's law. So we calculate the fluid velocity there, and then we import the data in that velocity field entry. And then with these other setups, what we need to do is put in the fluid diffusion coefficient. We'll use 1 times 10 to the minus 9 meters squared per second. The porosity is the same variable that we used for Darcy's law. And so there it is. And we also have permeability here in Darcy's law. Now the way that we set that up is we define two domains. And in each domain, we have porosity and K. That domain is domain 2, which is the fracture domain, and domains 1 and 3 are the matrix, and you can see we have different values of porosity and permeability in those different domains. So we use the same variable name, porosity and K, to indicate those two variables, but we give them different values in different domains. So here's the concentration on the input, where concentration will be a concentration of 1. We start out with an initial concentration of 0, and we'll use a step function. We'll start out at a function or a concentration of 1, and then we'll step it down after 3 times 10 to the 7th seconds, and that'll allow us to look at what happens after a pulse enters a fracture and the bleed out. So the mesh is a little bit unusual here. This is a swept mesh, and I'll show you how to set that up. We're going to use a triangular mesh on the top, and then a swept mesh with the kind of distribute. Well, here you go. We'll set up the triangular mesh on the top, and then here's the swept mesh with the distribution that is shown there, and it's a distribution with variable sizes. And now we're going to extend the swept mesh into the fracture. And when I initially set this up, I put the distribution, which is set up here, but that distribution is for domains 1 and 3. But the fracture is domain 2, so I need to change the distribution. So I get rid of those. I'm just going to put 3 elements in the fracture, and they're going to have them evenly spaced. So we'll set that up. But what we've got to do is make sure that when we go to distribution, make sure that we've selected that domain too, and now we'll run it. We get 3 elements. These are parallel elements with that triangular shape or triangular element shape from the top that are projected down. And then here, this is a swept mesh with that distribution shown there for the bottom. So try the swept mesh, experiment around with those distributions to get a feel for how it works. So we're going to run this with a stationary simulation to do the fluid flow. The fluid flow will be steady, and then we're going to have a transient simulation for the transport, and we'll import that fluid flow. But we're going to need to change the boundary conditions because we're going to have flow coming in at a concentration of 1 until 3 times 10 to the minus 10 to the 7th seconds, and then we're going to stop the flow abruptly, and we're going to have clean flow coming in. So I'm going to change the concentration boundary conditions. I'm going to run this in 2 steps. The first step is going to be 0 to 10 to the minus, or 10 to the 3 times 10 to the 7th seconds, and that's set up with this exponential range. And then in step 2, that's going to start at 10 to the 7.3. That's 3 times 10 to the 7th, and it's going to go to 10 to the 9th. Okay, so I've got 2 steps, and I'm going to switch the boundary conditions. So this boundary condition is going to use that second concentration, and I'm going to go and turn off concentration 1 so I can use concentration 2. And we also need to see how we're set up with the values of dependent variables. So the initial conditions, we import that from the steady state analysis. The variables that we don't solve for, we import from steady state because that's the fluid flow. We're not going to solve for fluid flow here. And then in time 2, we're going to use the initial conditions will be from the end of the previous simulation. So really we're doing 2 simulations here. One while the concentration's coming into the fracture, and then a second simulation where the 0 concentration or clean water is coming into the fracture. And then that third line, step 3, is where we combine those 2 solutions. So this kind of setup gives you a great deal of flexibility in how you do the analysis. In order to get this to work, we have to turn we're going to step the concentration down. Actually, now that I think about it, we don't really even need to do this. We don't need to have this step because we're switching the boundary conditions from that concentration 1 to the concentration 2. So we have this step here, but we don't really need it. Actually, we can set this up in a number of different ways, and so one way would be to use the step function, but here I'm showing you a different approach where we've got these 2 different solution steps set up for 2 different time ranges. So we run this. And then you can see the concentration coming into the fracture. You can see the time up there on the upper left. So matrix diffusion is coming in, and now we have clean concentration coming into the fracture. And so the concentration in the fracture is 0, and that slug of mass that came in starts to move away from the fracture and move back towards the fracture. And that's the matrix diffusion effect. So here's the concentration at a monitoring point. We've got a monitoring point down towards the end of the fracture. The mass is coming in from the left, and so that's a monitoring point for the flow. This is a monitoring point for the concentration, and then there's the flow rate at that point. And then this is the concentration at the monitoring point. You can see it's just a pulse. Remember, we cut the concentration off at 10 to the 3 times 10 to the 7th. If we look at it on a log scale, here's what it looks like. I'm going to change the scale a little bit. So you can see the pulse, but then for a long time afterwards, we've got the concentration decreasing, but it decreases slowly. Here's the cross section. You can see the purple, that's the first time step, and then the second time step as the mass is moving into the fracture and diffusing away. And then that's the profile where the mass is clean in the fracture. The mass moves away from the fracture, and then also it diffuses back. There you can see there's mass out in the matrix as it's diffusing back in the fracture, and that causes the sustained mass that shows up at the monitoring point downstream.